Today, in this video, we will see theorem of parallel axis. Moment of inertia of any given figure, see this figure, moment of inertia of any given figure about an axis which is parallel to the centroidal axis. Moment of inertia about this axis, x-axis, and which is parallel to the centroidal axis. This small x-axis is centroidal axis. Is taken as the sum of moment of inertia about the centroidal axis, sum moment of inertia about the centroidal axis, and the product of area and the square of perpendicular distance between the two axes. Area and square of perpendicular distance between the two axes. Moment of inertia of any given figure about an axis. See, calculate moment of inertia for this x-axis, for this x-axis. This much, this x-axis is equal to sum of moment of inertia about centroidal axis. This x-axis is centroidal axis, Ixx, plus product of area and square of perpendicular distance between the two axes. Between this x-axis, see this figure of area A, centroidal axis is x-axis and y-axis, and between this small x-axis and this x-axis, capital X-axis, distance is h. So square of this distance, product of area and square of this h distance, that means ah square. Moment of inertia of any given figure about an axis which is parallel to the centroidal axis. See, this is moment of inertia of any given figure. This is any given figure about an axis which is parallel to the centroidal axis. About this axis, capital X axis, which is parallel to this small x axis. It's taken as the sum of moment of inertia about centroidal axis and product of area and the square of perpendicular distance between the two axes. So now calculate moment of inertia for this y-axis which is parallel to this small y-axis, small y centroidal axis. Therefore, Iy is equal to moment of inertia of any given figure about an axis which is parallel to the centroidal axis. This centroidal axis is y-axis and parallel to this axis is y-axis. So moment of inertia about this capital y-axis is equal to sum of moment of inertia about the centroidal axis. But this distance is d between capital Y and small y centroidal axis, Iyy plus area of this figure A into distance between both this capital Y axis and small y axis is d, and square of this distance is theorem of parallel axis. Now next see theorem of parallel axis, how this equation comes. Let's see how this equation comes. Step by step we see it. So first see theorem of parallel axis. Consider here one small element, and this element is delta A. and this distance, this between this centroidal axis small x and this element distance is y, y1 distance. So consider here dix, moment of inertia dix. This is small element, this is whole area, and small elemental area is this small area, and this x-axis, capital X-axis, consider small part of this capital X-axis, and moment of inertia of this small part is this delta A into, here we see ix delta A into only moment of inertia about this small x-axis is this small element delta A into y1 plus h square. For this equation, for proving this equation, we have to take this figure, and now let's prove this equation. Dix, this small x distance, dix is equal to delta A into y1 plus h square. Dix is equal to delta A, and y1 plus h square is, sorry, y1 plus h, here not square, y1 plus h whole square, because this h distance we take square of this h distance. Dix delta A is equal to y1 plus h square, that means y1 square plus 2 y1 h plus h square. Dix is equal to delta A y1 square plus delta A 2 y1 h plus delta A h square. Now for considering this whole part of the body, total body, integrate this equation. Now integrate dix is equal to integration of delta A y1 square plus integration of delta A 2 y1 h plus integration of delta A h square. This d into ix, this d into ix is small part of this capital X axis. Now integration, that means total part, that means ix, total this x axis means ix. Ix is equal to dA into y1 square is this dA small part into y1 square, that means see moment of inertia about this small x axis, that means ixx. This moment of inertia about this small xx, that means ixx is equal to integration of dA into y1 square. See here, integration of dA into y1 square. That means this is moment of inertia about small x axis plus 2y1 h. Take this 2h common, integration of y1 delta I, and plus take this h square common, integration of delta I. Ix is equal to ixx plus this integration of small part of delta A. That means that means integration of small this delta A, that means total area A. That means see here h square into A, and this term is 0 because see here, next slide, this integration of y1 delta A is integration of y1 delta A. That means for this term explanation, see here, integration of y square delta A, multiply here A and denominator also A. For centroid find, we use formula, see, y1 a1 plus y2 a2 plus dot 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 y1 an upon a1 plus a2 plus an. But we already consider that our centroid lies on origin. See here, our centroid x-axis is lies on origin. So that's why this term is going to be 0 because our centroid lies on origin. This x-axis bit for this area, whole part of the body area, our centroid lies on origin. That's why we take this equation is this integration of y1 delta a 2h is 0, and here ix is equal to ix, that means I capital X, I small x plus a into h square, and see here I capital X is equal to I small x plus a square, and here I capital X is equal to ix plus a square. This is derivation of theorem of parallel axis. Here dix is equal to delta a plus y1 a square. We take directly moment of inertia. We use directly moment of inertia formula for this small x-axis. Dix is equal to delta a into y1 plus h square, and with the help of this we solve this. Ix is equal to ixx plus a square. So this is theorem of parallel axis. Thank you very much.